My name is Shi. I'm an associate professor at the Department of Mechanical Engineering. In our lab, we work on thermal engineering and nanofluidics. Nanofluidics refers to the study of transport of fluids in nanoconfinements, which has a great impact on biotechnology, medical diagnosis, and energy conversion systems. In comparison with larger scales, nanofluidic systems have a much higher surface-to-volume ratio, and therefore the fluid behavior is significantly affected by the surface properties. In the meanwhile, the physical properties of a fluid in nanospace can be quite different from their bulk values. For instance, due to the increased degree of orientation of water molecules in the vicinity of a charged interface, a higher activation energy is required for a water molecule to relocate to another position. In consequence, the apparent viscosity in nanospace becomes much higher than that of the bulk water. This phenomenon is called the viscoelectric effect. Other properties, such as the dielectric constant and boiling point, which can rise up to more than 300 degrees Celsius, also deviate from the bulk values. The investigation of these unique fluid properties and the flow behavior at the nanoscale is one of the central parts of our research interests. The flow in a nanofluidic channel can be driven by electroosmosis, which refers to the movement of an electrolyte solution under an electric field. When the channel surface is negatively charged, the counterions, cations, from the electrolytes will accumulate to the surface on the liquid side to satisfy electron neutrality. The tangential electric field to the surface drive the cations as well as the surrounding water molecules toward the direction of the electric field, generating the flow. As the electric field reverses, the flow direction is reversed consequently. Therefore, for conventional electroosmotic pumping in nanochannels, it can only be used by a DC electric field, which has bubble generation issues at the electrodes due to electrolysis. On this point, we developed a salt concentration biased nanopore system in which local charge can be induced in solution due to the separation of ions caused by the large electric field inside the nanopores. Interestingly, this induced charge inverses with the reversal of the electric field, and therefore the fluid can continuously move in a single direction for pumping even under an AC electric field. We term this unique phenomena transport-induced charge electroosmosis, which paves the way for AC electroosmotic pumping in nanofluidic systems. Another critical technology we are developing using solid-state nanopore is single molecule detection. We apply either an electric field or a solute concentration gradient in an electrolyte solution to drive biomolecules pass through a nanoscale aperture, where the former is called electrophoresis and the latter is diffuse seal phoresis. Not only the molecules but also the ions in the electrolyte solution are driven by the external bias due to the electromigration or diffusion, giving rise to an ionic current. The presence of molecules in the nanopore temporarily affects the ion transport. By tracing the ionic current variation, which is known as resistive pulse sensing, the structural information of the molecules can be revealed. Nanopore resistive pulse sensing can be applied to various biomolecules such as viruses, DNAs, RNAs, and proteins. And thus it has extensive applications for medical diagnosis. Currently, we are working on the development of DNA sequencing using solid-state nanopores due to its importance to realize the concept of precision medicine, which means the personalized medicine based on our genomic information. The conventional DNA sequencing method detecting fluorescent intensity of labeled molecules require amplification using polymerase chain reactions, PCR, which are time-consuming and label-intensive, largely reducing the efficiency. In contrast, nanopore sensing provides a simple way to directly detect each nucleotide on DNA molecules without amplification. However, biological pores used in the existing nanopore sequencing technology have a few shortcomings, including weak mechanical strength, low thermostability, and incapability of reading long molecules. On this account, we work on solid-state materials for the next generation of nanopore DNA sequencing. Particularly, we put our emphasis on two-dimensional materials with a thickness less than 1 nanometer to achieve ultra-high sensing resolution. Our research expands from fundamental studies to real applications. In addition to research development, our students have opportunities to involve in diverse activities for commercialization of our technologies, both domestically and globally. We look for and welcome young talents who are willing to take challenges and create innovation for a better and more sustainable future. So please join us.